Hello everyone. I am Himanshi Mishra, and I'm the PhD research scholar in the Department of Applied Mechanics, IIT Madras. And this week, I'm going to solve some problem related to the external flow field, the heat transfer due to the external flow field. So last week also, I have solved some problem related to the external flow field. So basically, we have looked some laminar flow problems. We use the Nusselt number correlation for the laminar flow, and we find out the heat transfer coefficient. And separately, we solve some problem related to the turbulent flow field as well. So for that, we actually use the Nusselt number correlation for the turbulent flow field, and we find out the heat transfer coefficient. This week, we will be solving problems related to the mixed flow. By mixed flow, I mean that the flow is laminar when initially when passes through the flat plate, but after some time, after passing through the some specific distance, it becomes turbulent in nature. So basically, we have a laminar flow, and after some time, we have a turbulent flow. So let's say this is my flat plate. Here, the flow is laminar, and after passing some distance, it becomes turbulent in nature. So we will be using the correlation of Nusselt number, which is valid for these kinds of flows. And then we will be solving for heat transfer coefficient or the heat rate. Then we will solve some problem related to the Chilton-Colburn analogy, where we define a relationship between the drag force coefficient and the heat transfer rate coefficient. So in the last week also, I have solved one problem related to that. We will look some more problems related to that concept. So if we have given the drag force or the drag force coefficient, we can find the Nusselt number or the heat transfer coefficient rate, and then we can able to find the total heat rate. And then we will look couple of problems related to the average heat transfer coefficient rate. We have already solved some problems related to that concept in the previous week, I think week 4 or 5. So let's begin with this class. So let's begin with the first question. So in first question, we have says that consider a flat plate subject to a parallel flow having the velocity of u infinity 5 meter per second and temperature is 20 degrees Celsius. Determine the average convective heat transfer coefficient, convective heat transfer rate, and drag force when the length is 2 meter and width is 2 meter for the white flat plate when air is flowing. So here air is flowing, and the surface temperature is given as 50 degrees Celsius and 80 degrees Celsius. And in the second part, we have a different dimension of the plate as well as the water is flowing instead of air. So we need to find the average heat transfer coefficient rate and convective heat transfer rate and the drag force when the water is flowing instead of air. So in this question, we have given two scenarios. The first scenario says that there is a flat plate and air is flowing flow past the flat plate. Dimension for the first part is given as this is my width and this is my length, and here if air is flowing in case A, in first part of the question, air is flowing having the velocity of 5 meter per second and temperature 20 degrees Celsius, and the surface temperature is given as 50 degrees Celsius as well as the 80 degrees Celsius. So let's find for the first case the heat transfer coefficient rate. So first we need to determine whether the flow is laminar or turbulent, or so for that we have to find the Reynolds number for the both case. So let me do the second case as well. this is my second case with water. So I have air and water in both the cases. So let's find the Reynolds number in both the cases to know whether the flow is in laminar or in turbulent state. So for the first case, let's say Reynolds number A. So the Reynolds number will be So I'm using the viscosity of air. So it's just a property. So we can find the properties from any book or over the internet. So by calculating this, we will get Reynolds number 5.99 10 to the power 5. So the flow is turbulent in nature because the Reynolds number is more than the critical Reynolds number here. So in this case, I have found the Reynolds number when the temperature is 80 degrees Celsius. In that case, the viscosity will change, viscosity of air will change. And in the first case, the temperature is 50 degrees Celsius. So I have two different Reynolds number at two different surface temperature. So in the question, we have given the surface temperature 50 degrees Celsius as well as 80 degrees Celsius. So the properties of the air will change due to that, like density, viscosity. So I have found the two Reynolds number, let's say 1A and Reynolds number 2. One Reynolds number is for the 50 degrees Celsius and one is for the 80 degrees Celsius surface temperature. And in both the cases, the Reynolds number is more than the critical Reynolds number. That means the flow is in turbulent in nature. So I have a turbulent flow for both the cases. So we need to find heat transfer coefficient, heat rate, as well as the drag force. So let's find the drag force first. So the drag force is actually given by simple drag force relation from the fluid mechanics. So the density area, surface area, and the velocity is given. So density is just a property. So we know the density of air and density of water. We need to find the drag force coefficient here. So first we will find this drag force coefficient, and then we will find the drag force. So for the drag force coefficient, we will use the correlation for the drag force coefficient as So this is my correlation for the drag force coefficient. We already calculated the Reynolds number here, and then we just need to plug the value of Reynolds number in this correlation to find the drag force coefficient. Now on solving, we can get So this will be my drag force coefficient. And now we just need to put the value of drag force coefficient and remaining variables like density, surface area, and the velocity to find the drag force. So this will be my drag force coefficient 1 by 2. So I'm taking the density of air as 1.1 and the velocity is given by 5 meter per second. This is my area. So my drag force will be around 0.12 Newton approx. So this will be my drag force. So here we first calculated the drag force coefficient from the correlation I have defined here, and then we just put the value of Reynolds number here to find the drag force coefficient, and then we just found the drag force. Now let's find the heat transfer coefficient. So the correlation we will be using for the Nusselt number is given as So we will use this correlation of the Nusselt number when the Reynolds number is greater than this value. So we already got the Reynolds number of 5.99 10 to the power 5, which is greater than this critical value of Reynolds number. So that means the flow is not a completely turbulent flow, but it is in the transition region. So for that we can use a correlation for the mixed layer here. So we already know the Reynolds number, and Prandtl number is just depend on the properties of the flow, which we can easily get. So we just need to put the values of Reynolds number and the Prandtl number. So now by solving this, we will get the Nusselt number 604, and we know the relation between the Nusselt number and the heat transfer coefficient. So we can find the heat transfer coefficient rate from this. So my thermal conductivity of air is 26.9 by 2, and this will be my heat transfer. So it's quite a similar problem we have solved last week also. So there we actually use the correlation for the laminar flow as well as the turbulent flow, and here we are using the Nusselt number correlation for the mixed flow where there is a transition or both laminar and turbulent flow is present, because the Reynolds number is just above the critical Reynolds number, which is 510 multiplied by 10 to the power 5. And since we have already get the Nusselt heat transfer coefficient rate, we can easily find the heat transfer rate. So the Reynolds number I am using when the temperature of the plate is 50 degrees Celsius. So for that thing, my heat transfer coefficient rate is 8.13. So if I solve this, I will get so this will be my heat transfer rate. So we can again use we can use a similar analysis when the temperature of the plate is 80 degrees Celsius. So right now I have done the calculation when the temperature of plate is 50 degrees Celsius here. So earlier, if you remember that we have found the two Reynolds number. So this Reynolds number is for when the temperature of plate is 50 degrees Celsius, and this Reynolds number is when the temperature of plate is 80 degrees Celsius. So we have found the drag force, heat transfer coefficient relation, and the heat transfer rate when the Reynolds number is corresponding to the 50 degrees Celsius. So using a similar analysis, you can find the drag force and the heat transfer rate when the surface temperature is 80 degrees Celsius. So you just need to find the drag force coefficient CF, which is a function of Reynolds number. So here now you will substitute this value of Reynolds number. Then you will use the Nusselt number correlation for the mixed layer. Here also you will substitute this Reynolds number, and you will get the heat transfer coefficient H and Q, heat transfer rate, when the surface temperature is 80 degrees Celsius. So it is a similar analysis, just with different value of Reynolds number. Now we will solve for the second part of the question, when the flow is water. So until now we have looked when the air is flowing. Now there is water is flowing with same velocity and having the same temperature, but at different dimension of the plate. So now the dimension is 0.1 by 0.1. And we will use the same steps to find out the drag force, heat transfer coefficient H, and the total heat rate Q. It is just we have water now. The Reynolds number will change because the density of water is obviously different, way more than the density of air. So again, we can find the two Reynolds number here. One when the temperature of the plate is 50 degrees Celsius, and other when this Reynolds number when the temperature of plate is 80 degrees Celsius. So now we will use a property of water. So this is my kinematic viscosity of water. This is my Reynolds number when temperature is 50 degrees Celsius. Now, if my temperature increases, obviously the kinematic viscosity of water changes. The properties of the fluid got changes. And for that, I am directly writing the Reynolds number because we know how to find the Reynolds number. We just need to get the viscosity at that temperature. Kinematic viscosity of water at that temperature, and the Reynolds number in that case would be this 9 10 to the power 5. So we will be using the same correlation for the drag force coefficient as well as for the Nusselt number correlation. So I already defined the correlation for both drag force coefficient and the Nusselt number. So now I am directly putting this value inside the correlation. So I just need to put the value of Reynolds number here. is my drag force coefficient, and we know the formula of drag force. So I just putting the value like I have done earlier for the gas case. Density I'm taking is about 1000. This is my surface area, and this is the velocity. And if I calculate, I get the drag force as 0.62 Newton. Similarly, we will use the Nusselt number correlation when the Reynolds number is greater than this. So I will be using the same correlation for the Nusselt number and just directly putting the values. This is my Prandtl number. So this is my Nusselt number, and I can find the heat transfer coefficient rate here by putting the value of length of the plate as well as the thermal conductivity, and it will be around 9050. Now we know how to find the heat transfer rate. So basically I am following the same step that I have done for the air case. This will be 5430 watt. So for the air case, we get the heat transfer 1950 watt, and for the water case, this is my heat transfer, and for air case, this is my heat transfer. So we can imagine, like for the water case, the length is just 0.1 meter. And for the air, the plate was much bigger, of 2 meters. So even the plate is much bigger for the air case, and for the water case, the geometry of the plate is much smaller. We can see that still the heat transfer rate in case of water is much higher than the air. It's almost 4.5 times higher than that of air. So that is because the heat transfer coefficient for the water case is much higher than air, and so the heat transfer due to the convection not only depends on the surface area, that if you increase the surface area definitely your heat transfer rate will be increasing, but it also depends on the heat transfer coefficient rate, the properties of the fluid, the velocity of the fluid, and combining effect of all this determine the total heat transfer rate. So even if you have we see that we have a very small plate when the water is in the water case, when the water is flowing over the very small plate, the heat transfer is about 4.5 times higher than that of the air case. So let's go to the third question. We will solving the second question in the end. So in the third question, the top surface of a heated compartment consists of a very smooth and highly roughened portion, A and B, and the surface is placed in the atmospheric air stream. So in the interest of minimizing total convection heat transfer from the surface, which orientation 1 and 2 is preferred? So the surface temperature is 100 degrees Celsius and the air temperature far away is 20 degrees Celsius. The velocity of the air is given as 20 meters per second, and we need to find the convection heat transfer and the specific orientation. So we have given the two orientation here, orientation 1 and orientation 2. The B orientation is rough, and A part is actually smooth. So in first orientation, the air will pass through the smooth portion first, and then it becomes rough. And in the second orientation, the air will pass through the rough orientation first, and then it went smooth. So these are my dimensions. These are my dimension of the first orientation. 1. So in my first orientation, the initial part is smooth part, and when the air is flowing through the smooth part, it will be in the laminar region. Although the laminar or whether it is in laminar or turbulent depends on several factors, but we can assume that on the smooth part, the air is in laminar region, but as it reaches to the rough part, air becomes turbulent in nature. So we have laminar flow here, and we have turbulent flow here. So the turbulent is caused by the roughness of the surface. So when there is a flow past this rough surface, the flow becomes turbulent in nature. So for that, we will be using the correlation of a Nusselt number, which we have used in the previous question. So we need to find the Reynolds number. So this will be my Reynolds number. I just need to put the Reynolds number here. The Prandtl number is given from the properties of the flow. Sorry. So on calculating my Nusselt number, we get is 1366. Now we can obtain the heat transfer coefficient from this expression. Is 39.2 watt per meter square Kelvin. So now we can easily find the total heat rate by using the Newton's law of cooling. This is my surface area. This is my surface temperature, and this is the temperature of the air. So this Q will be (1568 watt). So we have solved the heat transfer coefficient and the total heat rate for the orientation 1 here. Orientation 1. So let's solve for the orientation 2. So we need to determine in which orientation there will be the more heat transfer. So we don't need to find the total heat rate. We just need to calculate the Nusselt number, and if we get that there will be more heat transfer rate, then the Nusselt number is higher. So we just need to calculate the Nusselt number here to determine in which orientation the heat transfer rate will be higher. because the surface area is the same in both cases, the temperature is same in the both cases, and therefore the total heat transfer will be determined by the Nusselt number or the heat transfer coefficient rate only. So just by calculating the Nusselt number, we can compare, we can directly compare in which orientation, either in one or in two, the heat transfer will be higher. So in one, I have said that the flow is laminar first, and when it reach to the rough patch, it become turbulent in nature. And for that case, we have used this correlation of the Nusselt number. But in the second case, so in the second case, there is a rough surface first. So air will encounter the rough surface first. That means air will become turbulent at the first patch itself. And when it reaches the smooth surface, it will still be the turbulent flow. So we will be using the Nusselt number correlation for the turbulent flow. So this will be my Nusselt number correlation for the in the fully turbulent case when the air is turbulent in entire region of the flat plate, unlike our previous orientation where the turbulence is in this rough patch only. So we will, in the second case, we will use the correlation for the turbulent flow, and if we put the value of Reynolds number, so Reynolds number will be the same, area will be the same, and temperature difference will be the same. In that case, we get the Nusselt number 2139. And for the case 2, we got the Nusselt number 1366. We solved for the Nusselt number for the case 1, for this case, and we got 1366 at that time. So the Nusselt number for the case 2 is higher than case 1. That means for the orientation 2, my heat transfer rate will be much higher than when I compare to this orientation. This is because the flow becomes turbulent initially itself in the first patch itself, and in the turbulent flow, my heat transfer coefficient rate or the H or the Nusselt number, which is non-dimensional heat transfer coefficient, is usually higher compared to the laminar flow. And this is what we found when we use the correlation. So after using the correlation, we found that the Nusselt number for the case 2 is much higher than the case 1, and therefore the heat transfer rate will be much higher in case 2 orientation compared to the case 1. So let's move to the different question. So this question, similar question actually we have solved last week. So this is almost the same question. I mean, and we will relate it. It is actually related to the Chilton-Carbon's analogy. So here the atmospheric air is in parallel flow, having the velocity of 15 meter per second and temperature 15 degrees Celsius. For the flat heater surface that is to maintain at a temperature of 140 degrees Celsius. So this is my temperature of surface. The heat surface area is 0.25 meters square and the drag force is 0.25 Newton. What is the electrical power? So we need to find the power, and we are given the drag force. So by using the Reynolds analogy, we can actually define the relationship between the drag force coefficient and the heat transfer coefficient. So we have given the drag force actually, not the drag force coefficient. So we need to find the drag force coefficient first, and then we can use the correlation which actually relate the drag force coefficient and the heat transfer coefficient. From that we will find out the heat transfer coefficient. So to find the drag force coefficient, I am using the simple drag force formula from the fluid mechanics. So I just need to substitute these values of force, density, cross-sectional area, and the velocity. Everything is given in the question. So since it is air, I am taking the density of air as 1 kg per meter cube. This is my velocity of air. So on calculating this, we will get drag force coefficient is 8.93 10 to the power minus 3. Now we will be using Reynolds analogy here. So here I am relating the drag force coefficient with the heat transfer coefficient. Cp is the heat capacity, and we already know the density is rho and u is velocity of air, and Pr is the Prandtl number. So now we can find the heat transfer coefficient here. And we just need to substitute the values. We already found drag force coefficient. So on substituting the value, we will get the heat transfer coefficient as and once we get the heat transfer coefficient, it is always easy to get the total heat rate. This is my heat transfer coefficient H. This is my surface temperature. This is the air temperature. And this will be my total heat transfer rate. So yeah, this is the answer. So in this question, we have given the drag force. So we first calculate the drag force coefficient using the simple drag force relation. And once we get the drag force coefficient, we can use the Reynolds analogy to find the heat transfer coefficient rate. This. And once we get the heat transfer coefficient, it is always easy to find the heat rate. So let's move to the different question. In this question, there is a circuit board with a dense distribution of integrated circuits in dimension of 120 by 120 mm. On a side is pulled by parallel flow of atmospheric air with velocity of 2 meters per second. From wind tunnel test, they determine the frictional shear stress on the upper surface, which is 0.0625 Newton per meter square. What is the power dissipation if the temperature should not exceed by 25 degrees Celsius? And the properties should be given at 300 Kelvin. So this is the similar problem, similar to the previous one. So we have a chip and we have given the shear stress tau, which is 0.0625 Newton per meter square. So we have given the shear stress. We can find actually the drag force here, and then we can use the drag force relation. This drag force relation to find the drag force coefficient. So using the same expression that I used in the previous question. This is my drag force coefficient relation, which is obtained from this expression. Now we need to find the heat transfer coefficient rate. We will use the similar Reynolds analogy. So we already know the drag force coefficient from this relation. So I will put the expression of drag force coefficient here in this. So I will get my heat transfer coefficient relation in terms of this shear stress and this specific heat capacity. So I just need to put this value here, value of shear stress and the properties of flow. This is my velocity. This is my shear stress. This is my heat capacity. And now I can find the heat transfer coefficient rate. To find the total heat rate, we know that this is my surface area. This is the difference between the temperature. So this is my heat transfer rate. So the question is similar to the previous one. We have given the shear stress and we can find the drag force coefficient using the drag force relation. So force is actually given as like shear stress multiplied by the surface area. So from this expression we can find the drag force coefficient, and by using the Reynolds analogy we can define the relation between the heat transfer coefficient rate H and this drag force coefficient. And once we get H, it is very easy to find the total heat rate. So yeah, similar to the previous problem only. So let's move to the different problem. So it's a true and false problem. So we just need to determine whether the statement is correct or not. So the statement says that if the fluid enters the tube at uniform temperature that differs from the surface temperature of the tube, the convective heat transfer occurs and the thermal boundary layer develops. In the thermally fully developed region, the shape of the temperature profile is preserved. So this is actually the correct statement. So the statement says that there is a tube. Let's say this is my tube, and there is a flow here at temperature T infinity, and the temperature of wall is Ts, and if temperature of wall differs from the flow temperature, there will be heat transfer rate, which is true because the convective heat transfer rate actually governs by the temperature difference. So this heat transfer rate proportional to the temperature difference. That means if my wall temperature is different from the flow temperature, there will be the heat transfer rate due to the convection. If my wall temperature is equal to the temperature of flow, that means the difference between the temperature is zero and there will be no convective heat transfer rate. Now for the fully developed region, by fully developed region, I mean that the temperature profile dot by dot x. So let's say this is my x direction and this is my y direction. So by fully developed region, I mean that my temperature will not change with respect to the x location. That means this dot by dot x will be zero. So there will be temperature variation. Some variation will be there. Let's say it is x, or which can be some constant or variable. Since the surface temperature and the air temperature is different, that means the temperature will vary along the y direction. So there dot by dot y will not be zero because there is a variation of temperature along the y direction, because this Ts not equals to T infinity. But in a fully developed region, the variation of the temperature in x direction, that means in the flow direction, is zero. There is no variation of temperature along the flow direction. That means my dot by dot x will be zero. Okay, so let's move to the seventh question. So I will solve the second question in the next class because the time is almost up, and I don't know if this Google Meet will be operating for more than 1 hour or not. So let's begin with the seventh question. So in the seventh question, the heat transfer rate per unit weight from a longitudinal section x2 minus x1 can be expressed as by this relation, where h12 is the average coefficient for the section x2 minus x1. So we have given the heat transfer coefficient rate for this region only. Consider the laminar flow over the flat plate of a temperature Ts. The spatial variation is given of heat transfer is given by this Cx power minus 1 by 2. Beginning with the heat convection rate equation, dq, which is given by this, derive an expression for h12 in terms of x1 and x2. So we need to actually find the heat transfer coefficient in terms of x2 and x1. So we have given the heat transfer rate expression as this we have already given. Now if we integrate this equation, we can able to find the total heat transfer rate Q. So in this patch, the heat transfer is dq, which is given for some hx. Now if we integrate dq, we can find the total heat transfer rate over the entire plate, which is span over from x1 to x2. we have a two equation now. So the total heat transfer rate is given already in the question by question 1, and we can find the total heat rate by integrating the dq, by integrating over this small, by integrating the small patch to the entire plate from x1 to x2. So we have a two equation. We can combine the two equation to solve for this h12. So we can equate equation 1 to 2 because both are heat transfer coefficient rate. The first equation is given in the question, and the second equation we actually find the total heat transfer rate by integrating the small heat element, small heat rate in the small element. This. So by combining 1 and 2, we will find equal to so by solving this, we will get so now we have already given heat transfer as Cx to the power minus 1 by 2. So we can put here so now we need to integrate this expression. So after integrating, we will get, so this is my relation of heat transfer in terms of x2 and x1 as well as some constant c. Now it is says that derive an expression for the heat transfer rate in terms of h1 and h2. So h1 is the heat transfer rate at x1 and h2 is the heat transfer rate at x2. So earlier we derived the heat transfer coefficient in terms of x1 and x2. Now we have to derive the heat transfer coefficient in terms of h1 and h2. So we can write equation 1 as this is my heat transfer coefficient. Let's say this is my equation 1. So this is just simple Newton's law of cooling. So I just subtract the heat transfer rate here for H2 with H1. Now I can again equate to equation 1 with equation 2 here. So I can equate equation 1 with equation 3. Now we are solving for this heat transfer coefficient. So on solving, we will get this relation. So this Ts minus T infinity will be cancelled by this. So we can take this Ts minus T infinity as a common outside the bracket, and this will cancel, and we will only left with x2 minus x1 and h2 x2 and h1 x1. So this is my heat transfer rate in terms of h2 and h1. So let's move to the different question, question 8. So this will be the last question for this session. In the question 8, we have given the Nusselt number. So experiment to determine the total local convective heat transfer coefficient for uniform flow normal to the circular discs have yielded a Nusselt number relation where N and A are positive. The Nusselt number and stagnation point is correlated in terms of Reynolds number and Prandtl number. Obtain the expression for the average Nusselt number corresponding to the heat transfer from the isothermal discs. Typical boundary layer development from the stagnation point yields a decaying convection coefficient with increasing distance from the stagnation point. So we need to find the Nusselt number here, and we have given the radial Nusselt number and the Nusselt number at stagnation point. So the stagnation point is the point where the velocity becomes zero. So when air is actually reached at the face of this tube, the velocity at the center will be zero, the flow will be stopped, and that will be my stagnation point. And for the radial surface, we have given the Nusselt number. For the stagnation point also, we have given the Nusselt number here. And we need to find the average Nusselt number over the surface. So at r equal to 0, the stagnation point is located here. So the velocity here will be 0, and this is my Nusselt number expression here. And for the whole radial surface, my Nusselt number expression is this. So I can find the total heat transfer coefficient. So as of now, this is my local heat transfer coefficient. I can integrate this to find out the total heat transfer coefficient, and from that relation I will find the total Nusselt number. So this is my expression to calculate the mean or the total heat transfer, average heat transfer coefficient. So since we are dealing with this cross-sectional area, it is just a circle. So the cross-section of the circle is pi r square. This is my r naught. So I will be integrating from 0 to r naught. And this is the Nusselt number we have given. So my local heat transfer rate will be so now I can put this relation here, and then I can indicate to find the total heat transfer coefficient. So now I have to integrate this. After integrating, I will get sorry. Yeah. So this will be my average heat transfer rate. Now I will use this average heat transfer rate to find out the total or the average Nusselt number. So earlier we used the local relation for the local heat transfer rate. Now we use the average heat transfer rate to find the average Nusselt number. So we already found the average heat transfer rate from the local heat transfer HR. So earlier we have given the local Nusselt number for the radial surface, and from that we got the local heat transfer coefficient HR. We integrate it to find the average heat transfer coefficient rate, and now we are finding the total or the average Nusselt number. So basically we are reversing our calculation. This will be my total Nusselt number that I obtain from this relation. So again I will repeat in case if you didn't follow this question. So we have given the Nusselt number over this surface, radial surface, which is the local Nusselt number. We found the local heat transfer coefficient rate by using this relation. So we found this HR. Then we integrate this local heat transfer coefficient rate to find the average heat transfer coefficient rate, and then we use a similar expression here to find the average Nusselt number, which is given in terms of constant A and N as well as the radius R and some Nusselt number at the stagnation point. So it is already given in the question, the local Nusselt number, and we actually found the average Nusselt number. So yeah, that's it for today. So next week we will probably look the interior flow field and the heat transfer due to the interior flow field. So I guess we are done with the heat transfer rate at the external flow field. So from week 4, I guess, we are solving the question related to the heat external flow field, particularly when there is a flow field above the flat surface. So we have solved several questions related to that. And if you want to go through this question, you can just look my notes, which I already uploaded in Drive. You can also visit my YouTube channel for revising those questions. So yeah, that's it for today.